These are the last notes for Chapter 9. We've done all sorts of significance testing. We've learned about power, type 1 error, type 2 error. So now it's kind of time to wrap things up. We're going to talk about using tests wisely. So in italics here it says carrying out a significance test is often quite simple, especially if you use a calculator or computer. Using tests wisely is not so simple. Here are some points to keep in mind when using or interpreting significance tests. So the first part here, how large a sample do I need? So we know a smaller significance level, like a smaller alpha, is going to require stronger evidence to reject the null hypothesis. In other words, to be able to reject the null hypothesis, we're going to need a smaller p-value. A higher power gives a better chance of detecting a difference when it actually exists. Right? So we like power, right? Remember, if a blood test is very powerful, it's a pretty good chance it's going to detect a difference in the blood, right? You're going to set it off. The third bullet here, it says, at any significance level and desired power, detecting a small difference between the null and alternative parameter values requires a larger sample than detecting a large difference. So if the difference between the null and reality, let's say is 0.5 versus 0.51, we're going to need a lot of backup. We're going to need a lot of support. So we'll need a larger sample in that case. And the next part here is statistical significance and practical importance. So when a null hypothesis, which is the no effect or no difference statement, can be rejected at the usual levels, alpha equal to 0.05 or 0.01, there is good evidence of a difference. But that difference may be very small. When large samples are available, even tiny deviations from the null hypothesis will be significant. So that's why it's important to have large samples. But then again, right, if we have a huge sample and we're having just tiny deviations and all of a sudden that appears statistically significant, is that really of practical importance to us? And so now we're kind of getting into how statisticians or people who know stats might use and abuse the results of a significance test. So the next part here says beware of multiple analyses. Statistical significance ought to mean that you have found a difference that you were looking for. The reasoning behind statistical significance works well if you decide what difference you're seeking, design a study to search for it, and use a significance test to weigh the evidence you get. In other settings, significance may have little meaning. We're going to look at that. So in other words, if you have a goal, right, you want to find a difference, like our first semester project, a lot of you had a hypothesis, you had a goal to look for a difference, and you stayed focused on that goal. You didn't start to look for other differences and claim there was statistical significance in some other form or fashion. So what really is the difference then between statistical significance and practical significance? So let's start with one we've harped on this chapter, statistical significance. Notice that's purely mathematical or theoretical, or you can think of it as being abstract, right? It's really just formulas. You give me a way to summarize the data and reflect on the data, and I decide whether it's statistically significant or not. I get a test statistic, and then I get a p-value, and then I make my decision. So practical significance would mean, like, how useful is this study, right? But we say practical significance is sort of fragile in the sense that statistical significance ignores a lot of things that are going on in the real world, right? It just uses a formula. Practical significance would be subject to things like sampling methods or poor design or outliers. So that's actually a lot more fragile. And notice the italicized part here. It says, the foolish user of statistics who feeds the data to a calculator or computer without exploratory analysis, which means graphing and taking a look at the data, right? So you could see things like outliers, will often be embarrassed. Right? So if you don't know the whole story behind the practical significance, right? What kind of sampling methods were used? Was there poor design involved? Can I take a graph of the data and look for outliers? Right? We really need to paint the entire picture and look at the whole story. So what's the problem with running multiple tests or multiple analyses? So the issue is this: when we have people analyzing the same data set over and over again, right? They're looking at the same data from different angles until they find something that would be statistically significant somehow. So these people didn't set out with a clear goal, right? They didn't set out with a hypothesis in mind to show that there was a clear difference, right? Something specific. They just take the data that's acquired and look at it from a bunch of different angles until they finally find something that is statistically significant. Well, right? That's the downside, right? That's the unethical part of these tests, right? Something that shouldn't be done, and it proves little about the situation, right? It would have little practical importance. So for a great illustration of this, right, the problem with multiple tests, look at the XKCD comic on the next page with the jelly beans. So it starts out with this claim, right? Jelly beans cause acne, right? And we get scientists to take a look at it, and it says we found no link between jelly beans. They did their research. Here's a statistician, no link between jelly beans and acne. The p-value was bigger than 0.05, right? So we couldn't find convincing evidence. In the next part here, it says, well, that settles that. I hear it's only a certain color that causes it. So if we put the scientists back to work and just notice the trend here, right? So there's no link between purple jelly beans, brown, pink, blue, teal, salmon, red. No link, right? The p-value is greater than 0.05 for all these different colors of jelly beans. So this is why this is wrong. They took the same data set. At first, they didn't care about the color of jelly bean that was supposedly causing acne, right? They just looked at jelly beans and saw if it had any link to acne. No link. But now they're taking that same data set and trying to look for different colors within the data set and find a link. Well, if we keep going long enough, and if you notice, they go through 20 colors here. And the only one that sticks out is they have something for the green jelly beans. I mean, which one is it? It was actually this one right here, the fourth one in the second to last row. So they finally got a p-value less than 0.05. And all of a sudden they're publishing saying green jelly beans are linked to acne. So if we look around long enough, I mean, they ran 20 different tests, right? They looked at it from 20 different angles and they tried to establish some sort of causation. So now it's pretty safe to say that this has little practical significance, right? And is really inappropriate and unethical from a statistics standpoint. And if you think about it, there's a 5% chance we're going to make a type 1 error anyway. So if you look at the data from 20 different angles, you can probably pretty well expect that you're going to get at least one error, type 1 error. So that's why this isn't trustworthy. But a great comic nonetheless. You guys know I like stats comics and stats memes. This site does a great job. All right, so example 1 is pretty much that exact comic. It says, suppose that 20 significance tests were conducted, and in each case, the null hypothesis was true, meaning jelly beans don't cause cancer. What is the probability that we avoid a type 1 error in all 20 of those tests? We're going to use a 5% significance level. Each individual test then would have a 0.95 probability of avoiding a type 1 error. So, what's the probability we avoid a type 1 error in all 20 tests? I know it's 0.95, right, for basically an individual test, because if alpha is 5% or 0.05, 1 minus that, right, not making a type 1 error would be 0.95. The probability we avoid a type 1 error throughout those 20 tests. So something I want to point out when we actually calculate this. Each of those tests is independent, which is nice, because that means we can just multiply the probabilities together. Okay, so first let's start off, let's be clear. Let's just take one test, for example. The probability we don't make a type 1 error, right? We avoid making a type 1 error in just one test would be 1 minus making a type 1 error, right? So 1 minus the probability that we make a type 1 error. But if you'll remember, that's just alpha. That's just the 0.05. So 1 minus alpha in this case would be 0.95. All right, so just to be clear about that, where that 0.95 comes from. But that's really just looking at one individual significance test. Now we have to apply that logic to 20 of these tests, right? So we have to do 1 minus alpha, right? you don't make a type 1 error for the first test, and then times the second test, and then the third test, and so on and so forth. We're going to do it for 20 tests, right? So remember, alpha is the probability we make a type 1 error. So we're trying to avoid it in 20 tests. So 1 minus alpha times 1 minus alpha 20 times. So if 1 minus alpha is 0.95, we can just do 0.95 times 0.95, or 0.95 to the power of 20. Which, drum roll please, what's the probability we don't make a type 1 error in 20 tests? It's actually only 0.3585. So about a 36% chance. That's actually, I mean, the majority of the time we would make a type 1 error if we ran 20 different tests. So the probability we avoid a type 1 error in all 20 of those tests is only 0.3585. All right, well, so then what's the probability that we make at least one error, right? They made one error in the jelly beans. Right? They finally found one that says green jelly beans. But what's the probability we make at least one error in 20 tests? And this is actually a really simple calculation. If you remember anything from chapter 5, probability. Like the probability you make at least one, think about the complement of that. That'd be 1 minus the probability that you don't make any errors. Right? That's the only case where you're not making at least one error. So we just found this. So that's just 1 minus 0.3585, which gives us 0.6415. So like I said, the majority of the time, you can expect to make at least one error if you're running 20 tests. So we have over a 64% chance of making at least one of these type 1 errors in 20 tests. So finding one significant result shouldn't surprise us. So that really gets to the point of why it's unethical. And if you look around long enough, odds are you're going to find something statistically significant. But very well could be by mistake, like green jelly beans causing acne. So that's the issue with multiple analyses. Now, the natural question would be, so how do we fix that? So how can we fix, we have 20 tests, and it's supposed to be 0.95, the probability that you avoid a type 1 error, right? It's supposed to be 0.95. Ours was only like 35%, right? 36%. How can we make it be 0.95? Well, we have these 20 tests to run, right? And each one is 1 minus alpha for the probability that we don't make an error. And there's 20 tests, right? Go down the line for 20. So if I think back to the original statement here, if I want to avoid a type 1 error in 20 tests, I really need to take this 1 minus alpha business and set that equal to 0.95. And then we're going to come up with what the true significance level would be that would get us through those 20 tests without making a type 1 error. So if I can take these 1 minus alphas and just set them equal to 0.95, that'll fix it. So I've got my 20 tests with no errors, right? 1 minus alpha, 1 minus alpha. That's the opposite of making a type 1 error each time. I'm going to set that equal to 0.95. Okay, and then how are we going to solve this for alpha? Well, if you do this 20 times, this would just be 1 minus alpha, that quantity, to the power of 20. Still equals 0.95. Then to get alpha by itself, we've got to get rid of this exponent, right? Let's take the 20th root of both sides. The 20th root. Check it out. I got it on the calculator here. So if I want to take the 20th root, I'm going to type in 20, and I'm going to go to the X root button. So if you just go to math, right, hit the math button, and then go down to the 5th one here. See it says the X root? That'll take the 20th root for us. So pick the 5th one down there. Now we have the 20th root, and we're supposed to type in 0.95. 0.95. Bingo. Which gives us 0.9974. So 20 through to that, we've got 0.9974. And then the 20 through to here, now we're free of the exponent. So the exponent and the root canceled out. We just have 1 minus alpha equals 0.9974. So subtract 1, divide by a negative, we get alpha equals 0.0026. Holy cow, that's a small alpha level. But think about it, that's what the alpha level would have to be across all of those 20 tests if we still wanted to be 95% avoiding a type 1 error. Right? So before, when it was 0.05, it was way too, we ended up getting a 35% chance. So those jelly bean people would have to be way more picky with their alpha level if they still wanted to keep that 95% probability across those 20 tests. So that actually makes the significance level crazy low if we wanted to keep that probability of avoiding those type 1 errors at 95%, which would be the ethical thing to do, by the way, if we were truly going to run 20 different tests on the same data. All right, so we've talked about the good, the bad, and the ugly when it comes to significance tests. That's all for these notes. That's all for Chapter 9. I'll see you in class.